by mass, there is now more invisible plastic floating in the ocean than visible trash.
Yeah.
And right now, as you are listening to this, it is passively passing through your blood-brain barrier.
It's a sobering thought.
Welcome back to Insight. Whether you are prepping for tomorrow's meeting, avoiding sleep, or just deep into a 3 a.m. tech binge, you are exactly where you need to be. While we melt your brain with today's breakdown, kick back, zone out to the background visuals, and just absorb.
Absolutely.
And speaking of visuals, you might notice the backdrop behind my co-host today is slowly shifting from like a crystalline molecular structure into this glowing deep sea abyss.
Yeah, I mean, it's setting the mood for a pretty massive reality check today. We are looking at a topic that sits right at the intersection of, cutting-edge biotechnology, brutal global economics, and this ecological paradox that is, well, it's fundamentally rewriting our understanding of the ocean and human neurology.
Right, so today we're tracking a scientific discovery that started in a literally dirty Japanese recycling plant. It promised to solve our global plastic crisis, but instead, it might accidentally poison the human brain.
Yeah.
We are going to explore the physical limits of ocean cleanup, dig into some incredible AI-designed enzymes inside industrial bioreactors, and then see how this all leads to a massive geopolitical showdown over global regulations in 2060.
And honestly, the craziest part is how every single piece of that puzzle connects.
It really is. So let's start at the inciting incident. The year is 2016. Scientists are digging around in a highly contaminated Japanese recycling facility, and they discover this bacteria called Idiionella sarchensis.
Right.
And just to ground this, we are talking about a mesophilic bacteria, meaning it's just a typical soil microbe that thrives in moderate everyday temperatures.
Yeah, exactly. But the evolutionary pressure in this totally carbon-starved environment forced this microbe to use polyethylene terephthalate.
Wait, that's the full name for PET, right?
Yes, polyethylene terephthalate, or PET. It's the absolute most common packaging plastic in the world. And this bacteria started using it as its primary food source.
Which is wild.
It is. And the mechanism here is what really sent shockwaves through the scientific community. The bacterium uses a highly specialized synergistic 2 enzyme system.
Okay.
It starts with the primary biocatalyst, which they called PTES. This enzyme specifically targets and cleaves the ester bonds of the crystallized plastic.
Like chemical scissors?
Exactly like molecular scissors. When it snaps those bonds, it liberates these soluble intermediate chemicals.
Right.
Specifically, one called mono-2-hydroxyethyl terephthalate.
Oh, wow.
Yeah, quite a mouthful. For the sake of our sanity today, we are just going to call that MHET.
Thank you for that, seriously.
So very welcome. It also releases smaller amounts of bis-2-hydroxyethyl terephthalate, or BHAT, and terephthalic acid, which we can abbreviate as TPA.
Wait, so let me get this straight. It's not actually eating the plastic like a dog eats a bone. It's using those chemical scissors to snip the solid polymer into smaller soluble pieces.
Precisely. It's a chemical dismantling. And then the second step of the mechanism kicks in. The secondary enzyme, called M-utase, acts as a precision tool. It binds specifically to that MHET intermediate we just talked about, and it cleaves it down into its absolute base constituent monomers.
Which are?
That TPA we mentioned, and ethylene glycol, or EG.
Okay, got it.
Once the plastic is broken all the way down to TPA and EG, the bacterium transports those base chemicals across its cellular membrane, consumes them, and the end product is literally just carbon dioxide and water.
Okay, let's unpack this. Because if nature already built this incredible molecular shredder that turns our water bottles into harmless CO2 and water, why do we still have a garbage patch the size of Texas?
Right.
Like, why hasn't this bacteria just multiplied and eaten all the trash in the ocean?
Well, it comes down to the physical properties of the plastic itself. See, that wild-type PTase enzyme from 2016 is severely constrained by heat.
How so?
Because it's from a mesophilic bacterium, the enzyme permanently deactivates. It essentially dies at temperatures over 40 degrees Celsius.
Oh, I see.
But to actually break down plastic efficiently, the ambient temperature needs to approach its glass transition point, which is about 65 degrees Celsius.
That's the temperature where the rigid plastic finally softens up.
Right. The heat loosens the polymer chain enough for the bulky enzyme to actually dock into it and do its job.
Okay.
At room temperature, the natural enzyme is so slow, it basically loses its ability to degrade the plastic in just a single day.
So nature gave us the blueprint, but physics kind of got in the way.
Exactly.
It was just too cold to be useful.
Yeah, and that gap is what triggered the deep learning leap in biotechnology. Scientists turn to computational biology and 3D machine learning, specifically using an AI algorithm called MUT-compute.
Well, then how does an AI algorithm actually fix a biological enzyme? I mean, it's biology, not code.
Well, it analyzes the 3D folding structure of the protein. The algorithm identifies the specific weak points where the enzyme starts to, physically unravel when it gets too hot. Then it suggests exact point mutations to stabilize those weak areas. It essentially codes in artificial disulfide bonds.
Like molecular staples to keep it from melting apart.
That's a perfect way to visualize it. By locking the structure with these artificial bonds, scientists engineered heat-resistant superenzymes like phosphatase and LCC-ICCG.
And those can take the heat.
Yeah, these variants survive perfectly between 50 and 72 degrees Celsius.
That's incredible.
It really is. In a lab environment, these AI-designed enzymes can turn 98% of highly crystallized post-consumer plastic back into base monomers in just a matter of days.
Okay, so if we have these heat-resistant AI-designed superenzymes, why aren't we just crop dusting them over the ocean right now? I mean, problem solved, right?
And that assumption right there is incredibly dangerous.
Oh.
It brings us to the terrifying reality of incomplete breakdown.
What happens?
Well, when you introduce enzymes or microbes to plastic without that required high-temperature environment, they don't have the thermodynamic energy to cleanly depolymerize the crystallized core of the plastic.
Because it hasn't softened up yet.
Exactly. So they just gnaw at the weaker amorphous edges. And when you unevenly chew on the edges of a macroplastic, say a floating bottle, you destroy its structural integrity. It shatters.
Oh, wow. It shatters into microplastics.
Far smaller, actually. It shatters into nanoplastics.
Wait, really?
Yeah. We are talking about synthetic polymer fragments smaller than 1,000 nanometers.
That is tiny.
To give you an idea of the scale, a 2026 expedition by the research vessel RV Pelagia sampled deep waters all the way from the Azores to the European continental shelf.
Yeah.
And they discovered that the ocean's missing plastic pollution hasn't biodegraded safely at all. Like you said at the start of the deep dive, by mass, there is now more invisible nanoplastic in the ocean than visible floating trash.
Because they're basically the size of viruses.
Exactly. And because of that microscopic scale, they entirely bypass standard biological filters.
Right.
The most alarming data point came from a toxicological breakthrough spanning 2025 and 2026. These nanoplastics are breaching the blood-brain barrier, or the BBB.
Okay, we need to pause there for a second. Let's make sure we explain the BBB.
Sure. Before we go further, it's vital to understand the blood-brain barrier is a highly selective, semi-permeable cellular boundary. It is designed by millions of years of evolution to protect your central nervous system from blood-borne pathogens and heavy metals.
It's the ultimate firewall for the human brain.
Right. It is incredibly hard to penetrate. But advanced molecular dynamic simulations prove that these nanoplastics have a property called extreme hydrophobicity.
Meaning they intensely repel water.
Exactly. And because of this extreme water repulsion, they literally dissolve into the lipid bilayers of the BDB.
Yeah.
They passively permeate right through that firewall and disperse directly into delicate neural tissue.
Here's where it gets really interesting, but also kind of terrifying.
Yeah.
If we listen to the hype, right, and we just quote-unquote wild release billions of plastic-eating bacteria into the cold ocean right now, we aren't cleaning the water.
No, we're not.
We are weaponizing floating trash into a neurotoxic cloud. We're just accelerating the timeline of turning visible macro trash into microscopic seeds of neurological damage.
And the human health data backs up that concern entirely.
I was afraid you were going to say that.
Yeah. Analysis of decedent human brain tissue from 2024 showed nanoplastic concentrations were 50% higher than identical samples taken just 8 years prior.
Wow, 50%.
This material is rapidly accumulating, and once inside the brain, toxicologists confirmed that these jagged, highly crystalline physical shards act as a nucleating seed.
Okay, what does a nucleating seed mean in a biological context? Like, what is it actually doing in the brain?
Imagine a microscopic, jagged rock floating in the brain's fluids. It provides a reactive scaffold that physically triggers the misfolding and clumping of endogenous proteins.
Which proteins?
Specifically amyloid beta and alpha-synuclein.
Oh, man.
Yeah, those are the primary molecular signatures directly linked to Alzheimer's and Parkinson's diseases.
That is, wow.
The data showed brain tissue from dementia patients contained up to 30 times the concentration of nanoplastics compared to healthy controls.
Okay, so wild release in the ocean is an absolute biological nightmare.
Completely.
Let's look at the thermodynamic limits then. Why exactly is an ocean cleanup mathematically impossible, even without the neurotoxic risk?
It all comes back to heat.
Right.
The global ocean is fundamentally a freezing environment. I mean, while equatorial surface water might hit 20 or maybe 28 degrees Celsius briefly, the vast majority of the ocean averages a mere 4 degrees Celsius.
Which is basically refrigerator temperature.
Exactly. Now, scientists have found naturally cold active enzymes, like one called PT30, that actually work at 4 degrees.
Oh, really?
Yes, but the thermodynamic trade-off is brutal. Their reaction speed is just incredibly slow. To do the degradation work that a heat-loving enzyme achieves in days inside a 68-degree tank, a cold active enzyme in the ocean would need multiple decades, if not centuries.
So, trying to dissolve the Pacific garbage patch with ocean temperature enzymes is like trying to melt a candle by breathing heavily on it from across the room.
That is a very accurate analogy. You're just not putting enough thermal energy into the system to cause the reaction.
Plus, if you dump enzymes into the open ocean, you have the massive dilution problem.
Oh, for sure.
Ocean currents would wash those extracellular enzymes away instantly before they could even dock onto a floating bottle.
Which is why the only viable scientific consensus relies entirely on highly controlled, closed-loop industrial bioreactors.
Okay.
You need heavily engineered facilities where the temperature, the pH buffers, and the enzyme concentrations are perfectly managed.
Right, taking nature's tech and putting it in a highly controlled box.
Exactly. And right now, a French biotechnology firm named Carbios is leading this. They are building a massive commercial plant in Longlaville, France, capable of processing 50,000 metric tons of complex plastic waste annually using these heat-tolerant superenzymes.
50,000 tons.
Yep.
Okay, so we have a solution that doesn't create neurotoxic nanoplastics.
Yes.
What's the catch?
The catch is the capital expenditure, or CapEx.
Ah, of course. The money.
Always the money. Establishing a closed-loop supply chain requires staggering upfront investment. The capex for the Longlaville plant alone is estimated at 230 million euros.
Wow.
And historically, getting funding for that has been nearly impossible. Because virgin plastic, the brand new stuff, is synthesized directly from petrochemical feedstuff.
It's basically just solid oil.
Exactly. About 60% of virgin plastic production costs are tied directly to oil and natural gas. And because digging up fossil fuels has historically been incredibly cheap, new plastic was always cheaper than recycling it.
Right. The oil companies already have their infrastructure built.
Exactly. The multinational petrochemical companies have these massive, deeply optimized global supply chains. Meanwhile, recycling is burdened by expensive labor, fragmented collection logistics, manual sorting, cleaning. It was never a fair fight.
But then early 2026 happened, and the math finally broke.
Yes, it did. Severe geopolitical conflicts in the Middle East triggered an extreme global energy shock. The price of Brent crude oil spiked to $119 a barrel.
That's a massive spike.
Massive. And because virgin plastic is so reliant on those petrochemical feedstocks, its price skyrocketed to $1.87 per kilogram.
Okay, so virgin plastic gets wildly expensive.
Yes. And at the exact same time, biorecycling technology achieved critical process optimizations. Scientists figured out how to use ammonium hydroxide pretreatment.
Wait, how does that speed things up? I thought the enzymes were doing the work.
They are, but the ammonium hydroxide essentially acts as a swelling agent. It physically expands the rigid plastic matrix so the bulky enzymes can physically fit inside and access the ester bonds much faster.
Oh, that makes sense.
Yeah, this single optimization cut the time to fully depolymerize plastic down to just 50 hours, cleanly recovering the base chemicals.
And because biorecycling doesn't rely on drilling new oil, its price isn't chained to crude oil shocks.
Right. So while virgin plastic hit $1.87, the price of advanced enzymatic recycled polyethylene terephthalate, or RPET, dropped to $1.51 per kilogram.
Okay, and that is the ultimate aha moment for you listening right now. For the first time in industrial history, engineering an AI-designed enzyme to dissolve old plastic in a giant hot vat became fundamentally cheaper than synthesizing new plastic from scratch.
Exactly. Because biorecycling just became cheaper than drilling oil, the entire geopolitical argument of the petrochemical industry just fundamentally shifted.
Which brings us to the 2060 outlook.
Yes.
So what does this all mean for the future of the planet? If the tech works and it doesn't create nanoplastics in a closed loop, and the money finally makes sense, what is the holdup?
Well,
Let's talk about the Intergovernmental Negotiating Committee, or INC.
Right. In February 2026, the UN convened INC 5.3 in Geneva to negotiate a legally binding global plastics treaty.
Yeah.
And to look at this impartially, as we do, we have to understand the two deeply opposed factions here. On one side, you have a coalition of over 100 developing nations and environmental scientists.
What's their core stance?
Their argument is mathematically straightforward. They demand hard, mandatory caps on the production of virgin plastic. They were pushing hard for extended producer responsibility, or EPR, meaning the companies making the plastic are financially responsible for the end of its life.
Right.
Their stance is that without turning off the tap at the source, any downstream waste management is basically futile.
Their core philosophy is basically more plastic production means more plastic pollution, which logically is hard to argue with.
True. But conversely, on the other side, you have oil exporting and heavily industrialized nations.
And what's their play?
They utilize a procedural mechanism called the consensus trap, meaning they require unanimous agreement to actively block any binding limits on the extraction of fossil fuels for plastics.
Ah, I see.
They argue that production caps would trigger severe global supply chain disruptions and carry massive economic costs.
So let's talk about how the biotechnology we've been breaking down today actually factors into this political standoff.
Well, environmental advocates argue that this new tech is creating a massive greenwashing moral hazard.
How so?
They point out that industry lobbyists are heavily promoting this end-of-pipe downstream biorecycling tech as the ultimate solution.
Oh, I get it.
Yeah. The industry's argument is essentially, if biotechnology can infinitely return plastic to its virgin monomer state inside these French plants, then there is absolutely no need to impose regulatory limits on how much virgin plastic we produce today.
Wow. So the opponents are arguing that the petrochemical industry is actively using the existence of these amazing enzymes to provide the sociopolitical cover necessary to keep the linear flow of fossil fuels uninterrupted.
Yes, they are using the promise of future circularity to justify current extraction.
And that brings us to the unforgiving math of 2060. Let's actually look at the numbers.
Please do.
That's state-of-the-art Carbios plant in France. It costs 230 million euros, takes years to build, and processes 50,000 tons of plastic a year.
Right.
But in 2024 alone, global humanity consumed 500 million metric tons of plastic.
500 million.
And because the UN treaty talks failed to cap virgin production, global consumption is projected to hit a staggering 1.2 billion metric tons by the year 2060.
And there's the wall we hit. The super enzymes are scientifically incredible. The closed-loop bioreactors are thermodynamically sound and, as we saw, increasingly profitable.
Yeah.
But mathematically, they cannot outpace an exponential production curve of that magnitude. Building enough 50,000-ton capacity plants to process 1.2 billion tons of waste is just economically unfeasible in that time frame.
Which raises an incredibly vital question for everyone listening.
Yeah, and this is the thought I want to leave you with today. If the existence of these closed-loop bioreactors provides the petrochemical industry with the exact sociopolitical cover they need to triple plastic production by 2060, will our pursuit of a perfectly circular recycling economy inadvertently guarantee that the deep ocean, the freezing environment where these enzymes can never survive, becomes permanently saturated with neurotoxic nanoplastics?
Man, that is a chilling thought to leave you with. While we try to scale up the solution on land, the sheer volume of production means the ocean just continues to shatter the excess into a toxic, invisible cloud.
It's a race against time, really.
We want to know what you think about this. Drop your hot takes down in the comments. Are you more worried about the UN treaty gridlock or the nanoplastic threat crossing your blood-brain barrier? Thank you as always for tuning into Insight. Keep questioning everything, and we'll see you on the next Deep Dive.